Over the next few videos, we're going to expand some of the ideas we've seen in 2 dimensions to 3 dimensions. In order to do that, in this video, we'll take a look at some fundamental ideas we need within a 3D coordinate system. We'll see in this video that we can extend familiar 2D geometry into 3D. In particular, we'll look at what both points and vectors look like in 3-dimensional space. We'll also examine some simple planes in that space, and we'll look at expanding the idea of circles from 2D into spheres in 3D. In order to denote a point in 3D space, we're going to need 3 coordinates instead of 2. So a point is going to be written in the form x, y, z, where each of those coordinates measures distance along an axis. So instead of just an x and y axis, now we have an additional z axis. 3D space then is going to allow us to take ideas from 2D space like lines and curves and expand them into surfaces and solids. The distance formula can be expanded fairly straightforwardly into 3-dimensional space by just adding on a third term. Remember that distance in 2-dimensional space is the difference between the y-coordinate squared plus the difference between the x-coordinate squared, and then we take the square root of all of that. Let's see why we can expand this. So I'm going to do my very best to draw in 3 dimensions. This is not my forte, but I will give it a shot. So I have 3 axes here. The x-axis, the y-axis is pointing upward, and the z-axis, imagine that's pointing outward in 3 dimensions. I'm going to put a point here, P, and we'll call that x1, y1, z1. And then I'm going to put some other point in my picture. We'll call that q. Let me move q over actually a little bit, just to make the drawing a little bit easier. So this is x2, y2, z2. And we want to find the distance between those two. So we'll call this length here of that segment, this straight line segment connecting them, d. What we can imagine is, let's imagine we drop a perpendicular down here to some point. We'll call it r. Where this line segment that I just drew, that lives in the xy plane. So that the coordinates of r have the same x and z coordinates as the point P. So this is going to be x1, we don't know about y yet, and z1, since it lives in the xy plane. And you can see we moved over the same distance in the x-axis and moved out the same distance in the z-axis as we did for P. Similarly, if we connect this to r and q, then we can see that r has the same y coordinate as q. So it has the same x coordinate and z coordinate as P, and has the same y coordinate as q when we draw that segment. So its coordinates are x1, y2, z1. This segment right here, its length, because r and p live in the same xy plane, that distance is just going to be, the length of that segment is going to be y1 minus y2, and we'll take the absolute value of that just to make it a positive number, because the x's and z's are all the same. And then down here, if we live in the same, since we're living in the same 2-dimensional space here, this distance, we'll call this d2. We're going to use the distance formula on that. That is going to be x1 minus x2 squared plus c1 minus z2 squared. So then we can use the Pythagorean theorem to say that d squared is d1 squared plus d2 squared. So d2 squared is y1 minus y2 squared. We don't need the absolute value since we square it, since it automatically becomes positive, plus x1 minus x2 squared plus z1 minus z2 squared. And then we just get taking square roots of everything and just rearranging to put everything in alphabetical order. We get this distance formula in 3 dimensions. So hopefully the picture I drew, you can make some sense of that in 3-dimensional space. We can also think of that distance d in terms of vectors. So if we consider the points P and Q again and create the vector PQ, that's just going to be the vector x2 minus x1, y2 minus y1, z2 minus z1, so that the distance between the 2 points is then the magnitude of the vector connecting them. We can take ideas about lines from 2 dimensions and expand them to ideas about planes in 3 dimensions. In particular, we know that the line x equals 0 in 2-dimensional space represents the y-axis, and the line y equals 0 in 2-dimensional space represents the x-axis. In 3-dimensional space, the equation x equals 0 is going to represent the entire yz plane. Similarly, the equation y equals 0 is going to be all the points that have a y-coordinate of 0, which are all the points that lie in the xz plane. The equation z equals 0 is going to represent all of the points in the xy plane. We know that the line x equals a in 2-dimensional space is a vertical line. In 3-dimensional space, x equals a is going to represent something that is parallel to the yz plane. Similarly, in 2-dimensional space, y equals b is a horizontal line. In other words, it's parallel to the x-axis. In 3-dimensional space, the equation y equals b is going to be a plane that's parallel to the xz plane. And an equation z equals c is going to represent a plane that is parallel to the xy plane. We know in a 2-dimensional space that a circle is a set of all points that are a fixed distance r from some center hk. We can expand that to spheres. Spheres are going to represent in 3-dimensional space the set of all points that are a fixed distance r from some center h, k, l. And so the equation of a sphere is going to be x minus h squared plus y minus k squared plus z minus l squared is equal to r squared. And this just comes from a simple application of the distance formula, measuring the distance from every point x, y, z to the point h, k, l, and setting it equal to r. All right, we'll use some of these ideas now to do a couple of examples. So first, we're going to find the distance between the points p equals 1, negative 2, 3, and the point q equals 4, 2, negative 1. So the formula tells us that we just take the square root and then we subtract the first x minus the second x and square that. Then we take the difference of the y coordinates and square that. And last, we take the difference of the z coordinates and square that. So we get that our distance here is negative 3 squared plus negative 4 squared plus positive 4 squared, which is 9 plus 16 plus 16, which is the square root of 41, which does not, that's a prime number, does not simplify at all. All right, that one was pretty straightforward. We'll work a little bit harder to get this one. Here we want to find the equation of the sphere whose center is the midpoint of the line segment joining the points P, negative 2, 1, 4, and Q, 4, 3, 10, and that passes through the point P. So we know in order to find the midpoint, we just take the average of all of the coordinates. So the midpoint, we'll call it M, is going to be negative 2 plus 4 divided by 2, 1 plus 3 divided by 2, and 4 plus 10 divided by 2. Just taking the average of each of those coordinates. And so we get 1, 2, 7 as our midpoint. So that's going to be the center. So that's our H, K, and L in our equation of the sphere. We want to pass through the point P. So we need to figure out the distance between M and from M to P. So we can do that two ways. We can either take the distance from P to Q and divide it in half, or we can take the distance from M to P directly. I'm going to do the second of those. So the distance from M to P is going to be the square root of -2 minus 1 squared plus 1 minus 2 squared plus 4 minus 7 squared. So we get the square root of 3 squared plus 1 squared plus 3 squared, which is the square root of 19, and that's going to be our radius. So our sphere now has center 1, 2, 7 and radius 19. So our sphere is going to be x minus 1 squared plus y minus 2 squared plus z minus, that's not a 7, z minus 7. I keep trying to write that as a z. 7, there it is, squared equals r squared, which is 19. All right, we've got this other example here. We're going to describe the set of points that satisfy x squared plus y squared plus z squared minus 4x plus 6y minus 2z equals 11. So we know this is some three-dimensional surface because it's got x, y's, and z's in it. The way it's set up might indicate to us it might be a sphere. So what we're going to do here is I'm going to put the x terms together. So I have x squared minus 4x, and then I have y squared plus 6y, and then I have z squared minus 2z equals 11. And I'm going to try to complete the square to see if this thing is in fact a sphere. So to complete the first square, I take half of -4, which is -2, and I square that, add that on. So I'm going to put plus 4 there, which means I better do the same to the other side. For the middle term, take half of 6 and square that. So I'm going to add on 9 here. I'll do that on the other side as well. And then for the last one, I'm going to take half of 2 and add that on. So I get plus 1. My first set then factors as x minus 2 all squared. My second set factors as y plus 3 all squared. And my last set factors as c minus 1 squared. And that is going to equal 11 plus 4 plus 9 plus 1, which is 25. And so we see that this is a sphere. Its center is 2, -3, +1, and its radius is, since we have a 25 over there, that's r squared, its radius is 5. All right, we'll use what we know about planes in three-dimensional space in order to answer this last question, or this next question. So we want to write an equation for the plane parallel to the YZ plane, and through the point P equals 2, -3, 5. All right, so what do we know about this plane? Well, that is all the points. All the points in that plane have the same x coordinate. We can see here that since it has to go through this point, that the x coordinate must be x equals 2. And so that is, in fact, just the x equals 2 is going to be the plane that we need. Pretty simple. All right, wrapping things up. We saw here that 3D coordinates allow us to extend a lot of the ideas that we know from planar geometry. In particular, we can find the distance between 2 points situated in three-dimensional space by just adding on one extra term to the very familiar distance formula we've been using in two-dimensional space. And we can extrapolate from circles to spheres by adding a third term to our equation for a circle. And we're going to find throughout all of multivariable calculus that these ideas can be used when we're examining surfaces rather than the typical curves and lines that we've been doing in two-dimensional space.